Welcome back, everyone. So I think we have only 2 more weeks left. All your assignments have been graded, and even the regrade request should have been done by now. So the only thing that is currently active is the Kaggle competition. So I see that there are still few teams, like not a lot, but very few teams who haven't even made any submission. So it's not a good idea to wait till the last 2 days just make your submissions, because you don't know the quality of your solutions if you haven't tried sooner. And in terms of the report for the Kaggle competition, so I want to remind you again, probably it's written in the PDF already, there's a significant portion of your weightage for the report. Okay, so you could get a very low score in the competition even if you're rank 1 in the leaderboard if your report is not good. Okay, so give equal importance to the report. So the report is where you show your machine learning analysis skills, what kind of analysis did you do, what kind of feature reprocessing did you do, if you chose an algorithm, why did you choose that algorithm, right? So this is where we can know how much you have understood these things. So it is important that you write a good report and make sure that you have all the components in the report that was listed in the problem statement. Okay, so if you miss any of those components, you're going to get reduction in marks, and especially I don't want to see contribution statements we all contributed equally. Okay, so even if you all contributed equally, I want to know exactly the tasks that each one of you did. So it's a very generic statement if you say we all contributed equally, then we don't need that section. So write detailed contribution list. Okay, so that also carries some marks in your report. So don't write a very generic statement. So any questions about Kaggle? Yeah.
What if someone in the group did not contribute as much as the others? Does he get penalized or?
Well, you write it, so then we will consider that later.
Okay.
Okay, well, this is to catch these kind of things, right? So that's why we ask you for writing the contribution list. And also it really helps you with the self-reflection. Did you have a good team? Did you all contribute well enough for the course? So it's also a kind of self-assessment for you and your contributions. Okay, and about the finals, I think I have given a sample exam sheet. So I'm just curious, so was it a hard paper or easy paper?
Okay.
Yeah. So yeah, I think especially given the fact that last year was remote, also this year is going to be online. So we, for example, last year I took a lot of time to make sure that the questions are clear. So it's not in classroom, so you cannot ask doubts. And the same holds for this year too. So you cannot ask any doubts during the exam. And in fact, I think for the ML exam is on 18th, right? So it's not oral, it's ML. In fact, for your exam, I will be in the flight, so I cannot answer any questions. So usually questions will be very clear. Worst case, if you have any doubt, there should not be any doubts. So worst case, if you have any doubts, you should not post in Piazza or you should not email the TAs. Okay, so this is not an assignment. In extremely rare cases, you can write your doubt and assumption in the answer sheet. I'm going to read it. Okay, but don't use that as an excuse for every question. You cannot have your own interpretation of the question and then say I wrote the interpretation in the answer sheet. Okay, so questions have clear interpretation. In extremely rare cases, when there is a very genuine vagueness in the question, then I will accept your explanation. So otherwise, writing an explanation about your understanding doesn't mean that you can interpret the question in whatever way you want. But I will make sure that at the cost of redundancy, I will make sure that everything is well explained, so that there is no question about the questions during the exam. Okay. So Oh, also one last reminder, like, so there might be some of you who get the, I forgot the name of the exemption, like, but I did mention that in the email. Like, some of you might get exemption for like having extra time during your exam. I cannot accept those requests directly from you. Okay, so I should get an email with a list of students from the university. So which means it is your duty to go ask for the extension officially, like make sure that they send me your name. Okay, so if your name is not like given to me, then I cannot give you that extra time. So that's just a reminder. Okay, so let us get started. So far, like, I think we spent a lot of time, like probably the last few weeks, in neural networks, like, and then like we also talked about advanced optimization methods, and then we talked about dimensionality reduction, right? Like, so today we are going to see a new topic. So I always have a dilemma of whether introducing this in the beginning of the course or end of the course. Like, sometimes I feel this is too late to introduce Bayesian learning. Like, nevertheless, I think this is something that you should learn in the introductory machine learning course. Okay, so today we are going to talk about Bayesian approach for learning. Okay, so this kind of requires a different view of like whatever things that we have seen so far. Okay, now if I have to summarize like the general problem that we have been discussing in this course like for a long time now, like, so we have some data X, okay, and there is a decision process by nature which is making the prediction for Y, right? So our job as a machine learning like engineer or researcher is to come up with models which will try to mimic this natural process, right? Like, so let us just call this natural process, like, which is giving you the actual labels, right? Like, so let us just call that as del X. Okay, so del X is kind of like a natural decision process which takes the data X and gives you a Y. Okay, so now we don't know what this function is. Like, so it could be a random process, like, or it could be a deterministic process in the background, but it looks random to us because of the measurement errors and so on, right? Like, so like there is some process, we are not going to make assumptions. Okay, so far we made assumptions about the process, but today we are not going to make assumption about this process. Okay, this process is giving us the labels. Now, from our side, like, we have a model, right? Let's just call it model M. Okay, and this model has a bunch of parameters, right? Let's just call those parameters as theta. Okay, so if I have to summarize like all of like what we are doing in machine learning, like, so like we try to define a loss function. Okay, so this loss function takes both del X and theta as input. Okay, and tries to minimize, like we just convert everything into a minimization problem, right? Like, so like given a new problem, like our usual procedure is to come up with a loss function and then minimize this loss function, probably through gradient descent, right? Now, so far we did not pay too much attention to the nature of this loss function. We tried like looking at different loss functions like exponential error or like hinge loss, like, or logistic regression error, like least squares and so on, right? Like, so we did not focus too much on the characteristics of this loss function. Now let us try to understand what this loss function is trying to model, right? So this loss function has two parts. Okay, so one is theta. We don't know what the theta is. And the second term is del X, which is the process giving me the true labels. And we also don't know what this true process is, right? So in some sense, we are trying to minimize a term which has two inputs, like, or two arguments, and we don't know like both of these arguments. Okay, so now, so far in this course, like, so whatever like methods that we have seen, right? So they can be kind of categorized as one broad category of algorithms. Like, so we're going to call that as frequentist approach. Okay. Now in frequentist approach, like we are going to treat del x as random. Okay, so frequentist approach treats del x as random. Or in other words, I'm going to assume that the data is generated by a random process, and I'm trying to model this by using some parameter theta. Okay, there is no probabilistic interpretation for theta. Like, so my data is random. Now, if you go back and revisit statistical decision theory or empirical risk minimization, if you think about what was our expectation over, right? All the expectations that we wrote so far are over the data set, right? Like, so we were having expectation with respect to x comma y, expectation with respect to the data distribution D, right? So in some sense, like we were assuming that the data is random, but the parameters are deterministic, like they are not random. Okay, so this is what we have covered in empirical risk minimization or statistical decision theory. Okay, so in today's lecture, like we are going to talk about an alternate approach for learning. Okay, so which is the Bayesian approach. So in Bayesian approach, we are not going to treat data as random. Okay, data is given. Okay, we are going to treat the parameters theta as random. Is that clear? So we're going to assume that the parameters are sampled from a random distribution. Now, how can I update my parameters conditioned on the given data? Is that clear? Okay, so this is what we are going to talk today. Like, but before we get into the details of Bayesian approach, like, so first I want to talk about the parameter estimation problem in general. So when you use a parametric model for doing machine learning, okay, so then you actually have two inference problems there. Okay, so the first problem is to estimate theta that best explains the data. Okay, so this is what we call as learning, right? Like, so, like given some data x, estimate the theta that best explains this data. Okay, now there is also a second inference problem, like which we care about, like which is basically to calculate the probability for new observations given the past observations, right? Like, so now theta is kind of used in between. Like, so you take the old data, you learn a model theta, and you use the model with theta to make the new prediction, right? Like, so to calculate the probability of new observations, let's call it as x hat, given previous observations. Or in other words, like what is the probability of this new observation x given the past observation? Is that clear? Now, we're going to call the first problem, which is the problem of learning parameters, as the estimation problem. And we are going to call the second problem, which is the problem of predicting new examples given the past examples, as just prediction problem. Okay, I want to highlight that estimation is not our end goal, right? Like, our end goal is really prediction. Like, we are using estimation as a mean towards this end goal. Like, so you first estimate the parameters theta, and then use this parameter to make predictions. Is that clear? Any questions so far? Okay, so now let us consider any data set. Okay, so which is a bunch of 1 to capital mod x number of data points. Okay, now we are going to assume that x is random. Okay, x is random and independent and identically distributed. Okay, now I told you that, like in Bayesian approach, like we're going to consider theta to be random vectors as well, right? Like, so now theta is going to be dependent on whatever distributions that we consider, okay? Like for example, like if I assume my parameters come from a Gaussian, okay, then in this case, my theta is given by mu and sigma square. Okay, so I can assume any distribution for my parameters, and then like whatever the parameters of those distribution, right? Like, so those are my parameters. Now, when you have this probabilistic view, okay, so then you could ask, like, what is the probability of theta given that I have seen the data set, right? Now, this can be modeled using the famous Bayes law, okay? So now I can write P of theta given x as P of x given theta, P of theta divided by P of x. Okay, so if I have to translate this Bayes law, it is trying to calculate the probability of a specific parameter configuration given the data set. Okay, now this is given by, okay, well, let's just call this as the posterior probability. Okay, so this is given by P of theta, which is just my prior belief about the theta distribution. Okay, so we're going to call this as prior. Okay, and P of x given theta is something that we have already seen in MLE, right? Like, so when we did maximum likelihood estimation, like, so you're trying to maximize the likelihood, which is probability of x given theta, right? So this is the likelihood that we have already seen. Okay, now P of x, which is basically the probability of the data distribution itself, right? Like, so we're going to call this as evidence. Okay, now in some sense, if I start with a prior belief about what is my probability distribution over theta, then every time I see a new data point, I can compute P of theta given x, which is going to give me an updated belief about the posterior distribution. So after seeing the entire training set, I will have a new posterior distribution over theta, like, which is what I can use, like I will use to make predictions. Is that clear? Any questions so far? Okay. Now, with this new framework, like for learning, like where we consider theta to be random, let us revisit the standard maximum likelihood estimation that we have been using so far, right? If you remember our discussion on logistic regression, for example, like, so we were just maximizing the likelihood or log likelihood of the data, right? Now, let us see how this fits in this Bayesian framework. So the likelihood of the data is given as the probability of x given theta. Okay, so when I make IID assumption, this is basically product over all examples P of x given theta. Right? Now, often when we try to maximize the likelihood, like we will be maximizing the log likelihood instead of likelihood because there is a product here. So product could lead to numerical instabilities. Like, so we will just do, let us just call log of L as some scripted L. Okay. Now, the entire MLE problem can be then framed as finding this theta maximum likelihood, okay, which is basically argmax of theta log likelihood of theta given x. Okay, now I can expand this and this becomes argmax of theta summation over x belonging to x log P of x given theta. Okay. Now, so this is something that we have already done, right? Like, so like given any probabilistic model, we can compute this log likelihood and then we will maximize this like we'll find the theta that maximizes log likelihood by using gradient descent, for example, right? Like, or you could use Newton-Raphson if it is manageable. Now, so what happens after that, right? So once you have the theta, then you are going to make new predictions. Like, you're going to make predictions for the test data, right? Like, so now the probability of new data point x given the old data set, okay, is given by integral over theta belonging to capital theta, p of x given theta, p of theta given x d theta. Okay, so in the Bayesian approach, like, so when you treat your theta to be probabilistic, then whenever you want to make a new prediction, like, you should also integrate over all possible thetas. Okay, now as you can imagine, like, this is going to be a very complex equation, in the sense often, like, we work with like very complex data, like parameter distributions that, like, you cannot integrate that easily. Okay, so this is where the maximum likelihood approximation comes in. So what we do in MLE is, instead of finding the actual theta that has the best possible like prediction, like, we're approximating it with p of x given theta ML, and p of theta given x d theta. Okay, now this term that you see here, so this doesn't have any theta in it, so I can take it out. So this becomes integral, sorry, p of x given theta ML, integral over theta belonging to theta, p of theta given x d theta. So what is this integral? I'm integrating over all possible theta and summing the probabilities. So what would that sum be? 1, right? So this is 1. So this whole thing is 1. So it is just p of x given theta ML. Is that clear? So what maximum likelihood estimation is trying to do is, instead of taking the complete Bayesian approach, like where you have a distribution over theta and, like, you're trying to integrate over the distribution, like, so this is very costly. So maximum likelihood kind of approximates this by saying, okay, instead of finding a theta, like, which is the most optimal, like, so I'm going to find a theta which just maximizes the likelihood. Okay, and, like, I will directly use it to make the predictions. Is that clear? Okay, so, well, we have seen examples for maximum likelihood before. Okay, so however, we are going to see a very simple example today, which will be the running example for, like, various approaches that we are going to discuss today. Okay, so the running example that I want to use is a really simple experiment of just tossing a coin for n times. Okay, so I'm tossing a coin, but I'm going to toss a deformed coin n times. Now the coin is deformed, which means probably the probability of heads or tails is not 0.5. It could be something else, okay, because of the deformation and, like, change in the structure. Now, however, we are going to make an assumption that each trial is IID. Okay, and we are also going to make an assumption that the data is actually sampled from a Bernoulli distribution with some parameter p. Okay, so I'm modeling a coin toss by using a Bernoulli distribution. Okay, now this Bernoulli distribution has parameter p. So the probability, let's say c is equal to 1 is for head and c is equal to 0 is for tail. Okay, now the probability that c is equal to c given p is given by p power c 1 minus p power 1 minus c. Okay, so this is what this, like, the distribution Bernoulli of C given P is. Okay, we have seen similar things before, right? Like, so now this is just a compact way of saying when C is equal to 1, the probability of that is P. When C is equal to 0, then the probability of that is 1 minus P. Okay, so like substitute C is equal to 1 and 0, like you'll get those probabilities from this. Okay, now this is the likelihood, right? So we want to maximize the likelihood. Like the other way to do that is to just maximize the log likelihood. So the log likelihood is given by log of product of I is equal to 1 to capital N, P of C is equal to Ci given P. Okay, now log of product is just sum of logs, right? Like, so I can just write this as summation over I is equal to 1 to capital N log P of C is equal to Ci given. Okay, now this means I take a log of this particular thing. Okay, now let us say that in the data set which has n trials, okay, n0 trials have C is equal to 0 and n1 trials have C is equal to 1, such that n0 plus n1 is equal to capital N. Okay, for example, let's say there are 100 trials and let's say 60 of them are head, okay, and 40 of them are 0, sorry, or tails. Okay, in that case, like, so you have 60 and 40 as n0 and n1, like, so the sum is capital 100. Is that clear? So now this means that this probability value is going to be Pi for n1 times and 1 minus Pi for n0 times, right? Is that clear? So I can just write this as n1 times log PC is equal to 1 given P plus n0 times log P is equal P of C is equal to 0 given P. Is that clear? So this is basically n1 times log P plus n0 times log 1 minus P. This is my log likelihood. Now I just need to differentiate this and set it to 0, then I will get the value for P, right? So this is a really simple like derivation. Like, so we are interested in dou L by dou P, which is basically n1 times, when you differentiate log P, you get a P, plus n0 times, you differentiate log 1 minus P, you get a 1 minus P, and there is also a minus because it is 1 minus P. Okay, so and this is equal to 0. Okay, now n1 by P is equal to n0 by 1 minus P. Okay, so then 1 minus P by P is equal to n0 by n1. Okay, and 1 by P minus 1 is equal to n0 by n1. Okay, and okay, I'm trying to finish the whole thing here. So 1 by P is equal to n0 plus n1 by n1. Sorry, n0 n1. Okay, so which means P is equal to n1 divided by n0 plus n1. Okay, I will write the final thing here. So P is equal to n0 plus n1 divided by, sorry, it's opposite. It's equal to n1 divided by n1 plus n0, or in other words, P is equal to n1 divided by capital N. Okay, now, so we have seen exactly same derivation for Bayes, like naive Bayes, right? So if you want to calculate the probability of heads, then maximum likelihood basically tells you that out of 100 times, if you see head for 60 times, then the probability of the next toss being head is just given by the frequency. So it's 60 by 100. Is that clear? Now, let us see one example. Like for this, like let's say I did 20 trials. Okay, out of which it is head for 12 times and tail for 8 times. Now the maximum likelihood estimation of P is given by 12 by 20, which is 0.6. Is that here? Now, what are the limitations of this maximum likelihood solution?
If you have only one trial, it can be like completely skewed one way or the other.
Yeah, so if you have only one trial, let's say it's a head, then maximum likelihood estimation tells us that the probability of the next trial being head is 1. And the probability of it being head is like being tail 0, right? So like both are extreme probabilities and we know that it is not true. Okay, any other issues? So this is with respect to this coin toss example, that is good. But can somebody remember like what other issue that we saw about maximum likelihood when we were doing logistic regression? Or in general, like, so whatever methods that we have seen so far, right? Like, so what was the general issue that we were facing whenever you want to learn something? If you think about it, like almost all the approaches that we have seen so far is in some sense maximum likelihood approach. Okay. Because if you remember, like we also saw connections between least squares and maximum likelihood, right? Like, so minimizing least square error is actually equivalent to maximizing the log likelihood, right? Like, so in some sense, like all the methods that we have seen so far is kind of trying to just maximize the likelihood. And such methods always have the problem of overfitting. So when you are just focusing on maximize the likelihood of the data, so you have the risk of overfitting. Okay, so this is an example of overfitting, right? Like, so when you have only one trial and it is 1, your model is not being cautious enough. Like, so it is just directly overfitting to this one experiment and says that, oh, okay, so like the probability of next being head is 1, right? Now, how do we avoid overfitting? So if we go back all the way to our lecture on like avoiding overfitting, like, so I did mention there like that one option is to use other estimators. Okay, like, and I told you that we will see later. Okay, so we are going to see such estimators today. So we are going to see a couple of more estimators than just maximum likelihood. Okay, so and also like see how that is going to help us avoiding this problem of overfitting or in general coming up with better estimation. So the second estimator that we are going to discuss today is the idea of maximum a posteriori estimation. Okay, or in general map estimation. Now, the big difference between MLE and map is that map is going to allow you to include some prior belief on the parameters. Okay, so we're going to use the concept of prior distribution P of theta that we saw in the base rule, like for maximum a posteriori estimation. Okay, so now the theta map, okay, is defined as argmax of theta, probability of theta given x. Is that fine? Now, if I have to differentiate this with like MLE, right? Like, so in the case of MLE, like, so we had theta MLE was given by argmax of theta. Okay, probability of x given theta, right? So they are different in their philosophy in the sense like MLE is trying to maximize the likelihood of the data, but MAP is trying to like maximize the posterior distribution of theta given X. Okay. Now, how would I do that? Like, so I could just, we know the base rule, like for P of theta given X, right? Like, so I can write this as argmax of theta, P of X given theta, P of theta divided by P of X. Okay. So now you see that you're trying to maximize this term, but the denominator is not at all a function of X, right? Like the denominator is actually the data distribution. Okay. So we can just ignore that since we are only doing argmax. So this becomes argmax of theta, P of X given theta, P of theta. Okay. Now, let's say I take a log of this, just like how we took log for maximum likelihood, right? Like so, then this becomes argmax of theta. Okay. So log of AB is log A plus log B, right? So what is the log of the first term? It's log of the likelihood, right? So the first term is actually your maximum likelihood, like the likelihood that you see in the maximum likelihood. So it's L of theta given X, okay, plus log P of theta. Is that fine? Or in other words, argmax of theta, okay, summation over X belonging to capital X, sorry, log P of X given theta plus log P of theta. Is that clear? Now, what is the difference between this maximization process and maximum likelihood? There's only one difference, right? Like the difference is this term. So if you don't have this term, then you have just maximizing the log likelihood. So what MAP is trying to do is it is going to add some prior distribution about your parameter theta. Okay. So in practice, this prior can be used for many things. Like so, for example, let us say you have some prior knowledge about the problem. Then you can encode that prior knowledge in this probability distribution. Okay. Like let's go back to the same coin toss example, right? Like so, let us say that we have no reason to believe that it's not a fair coin. Okay, so if it is a fair coin, then the probability of head is 0.5, right? So then I could have a P of theta which models this belief that it is like that this coin is going to give a head with 0.5 probability. If you have such a prior belief, then when you are trying to like see the first experiment and the experiment is giving you 1, your probability will not change from 0.5 to 1 per head. Okay, it may probably change from 0.5 to 0.51 or 0.56, whatever the rate in which you are changing. Okay, so you will be shifted towards head, but not to the extreme like maximum likelihood. Is that clear? So in some sense, the prior distribution that you are having in MAP, it prevents overfitting. Okay, so this prior distribution, the prior can be actually used to encode knowledge if you want, and it is also useful for to prevent overfitting. Okay, now for example, like if you want to enforce Occam's razor, like if you want to come up with models which are simpler, okay, you can have a prior distribution over the theta which says, oh, I want simpler models. Okay, so we're going to see an example for that very soon, but this is one thing that you can do. Okay, now the maximum likelihood approach that we saw, right? So which was trying to model the probability of X given theta. That is an example for frequentist approach. Okay, it's frequentist because theta is not a random parameter, like random vector in MLE. On the other hand, okay, so MLE is more frequentist. On the other hand, MAP actually has a distribution over the parameters. So this is an example for a Bayesian approach. Is that clear? Now, when you have a probability distribution for theta, like P of theta, right? Now, this probability distribution is going to have its own parameters, right? Like, so every probability distribution has its parameters. Like for example, in the case of Gaussian, it is mu and sigma. In the case of Bernoulli, it is P, right? So when you have a prior distribution, like over the parameters, that actually has its own parameters. So let's just call those as alpha. Okay. So this parameter, like which is the parameter of the prior distribution, right? Like so this is your hyperparameter. Is that clear? Now, well, probably this is where the term hyperparameter comes from. Like we have seen hyperparameter for different algorithms, like, but this sounds more intuitive in the sense like you have a distribution over the parameter space. So that distribution at a meta level has its own parameter. So that is our hyperparameter. Okay. Now we can do the same thing that we did for maximum likelihood. Like, so what is the probability of new data points given the data? So this is given by integral theta belonging to capital theta, the P of X given theta map, P of theta given X theta, right? So the same thing. So even with map, we are still not doing the integration, okay? So we are approximating the integration by using theta map and taking that out. Okay, and the integral becomes 1. So we are still avoiding this integral, like by using this map approximation. It is just that this map approximation is better than MLE approximation. Okay, is that clear? Any question? Any question in the chat? Okay. Now let us see an example, like so the same running example, like but with map estimation. Okay. Now let's go back to the coin toss example. Now I want to add my prior belief that this coin is a fair coin. Okay, which means like I want to come up with a prior distribution over the parameter P of Bernoulli, okay, in such a way that there is maximum weightage for a parameter P being 0.5. Is that clear? Now, you should know a lot of distributions like to deal with these kind of Bayesian modeling. Okay, so can anybody think about a probability distribution, okay, which has a support from 0 to 1 because P can only take values from 0 to 1, right? Like so P is a probability. So like you have this Bernoulli, and this Bernoulli has some probability parameter P. Okay, now I want to this P is between 0 to 1, right? So we are looking for a probability distribution which has a support of 0 to 1, and I want this probability distribution to actually peak at 0.5. Do you remember any such distribution? I think it requires brushing up your probability skills. So one such distribution, like which has a support over 0 to 1, is beta distribution. Okay, so beta distribution, like the PMF of beta distribution is given as follows. Like it has parameters alpha and beta. So this is given by 1 over b of alpha beta, p power alpha minus 1, 1 minus p power beta minus 1. Okay. Now this is what the definition for beta or beta of p given alpha beta is, where the b function, okay, so also known as the beta function, is given as, but the beta function is defined with gamma function. Okay, so it's gamma alpha gamma beta by gamma of alpha plus beta, where the gamma function, so this is a gamma function, is defined as, in terms of factorials. Okay, so x factorial is gamma of x plus 1. Okay, so this is just a very recursive definition of what is a beta function. Okay, so for the purpose of this lecture, like, you don't need to understand exactly what this distribution is like modeled as. Like, so like what matters to us is that this beta distribution has a support of 0 to 1. Okay, now by varying this alpha and beta, you can have different like distributions between 0 to 1. Okay, so here is a bunch of possible beta distributions. Like, so one thing that you should remember is, like, if you set alpha is equal to beta, then the model peaks at 0.5. So you can see that, so this is beta is equal to beta of 4,4, and this is beta of 20,20. So the larger the number of alpha and beta, the stronger your belief that it is 0.5. Okay, so if I put 100, 100 for alpha beta, so this is going to become something like this. Is that clear? So when alpha is equal to beta, like, you have the distribution that you care about, but there are also a lot of other distributions that you can model. Like, so for example, when alpha is less than beta, okay, so you are leaning towards the left, and when alpha is greater than beta, like, you're leaning towards the right, and so on. Is that clear? So for our purpose, like, so for this coin toss example, like, we are going to set alpha is equal to beta is equal to 5, which is going to result in a distribution which has the mode at 0.5. Okay, is that clear? Okay, so I will finish this example and then we'll take a break. So now we want to maximize the map objective, right? Like, so the objective is log likelihood plus log p of p. Okay, and we want to differentiate with respect to dou p and set it to 0. So then we are going to get our answer. So okay, we should not have more noise, it will affect the recording. Okay, so now we already know the first part. So the first part is just the log likelihood. So we know that when we differentiate the log likelihood, we get n1 by p minus n0 by 1 minus p. Right? So this is something that we already know. Now, what is the log p of the beta distribution? So let's go back. So you see that the beta distribution actually looks very much like Bernoulli. Right? So the Bernoulli is of the form p power n0, 1 minus p power n1, something like that, right? Like, so similarly, this is also of the form p power alpha minus 1, 1 minus p power beta minus 1. There is a constant 1 by beta, but given that we are differentiating, the constant term is going to go to 0. So we just have p power alpha minus 1, right? So that is going to become plus alpha minus 1 by p, and 1 minus p power beta minus 1. So that becomes minus beta minus 1 by 1 minus p is equal to 0. Okay, so I just need to rearrange things now. So let us put all the p one side, all the 1 minus p another side. So this becomes n1 plus alpha minus 1 by p is equal to n0 plus beta minus 1 by 1 minus p. Okay, now I'm going to do the derivation quickly because I have done this just 10 minutes back. So 1 minus p by p is equal to n0 plus beta minus 1 by n1 plus alpha minus 1, and 1 over p is equal to n0 plus beta minus 1 plus n1 plus alpha minus 1 divided by n1 plus alpha minus 1. Okay, so my p map is given as n1 plus alpha minus 1 divided by, so I can just put these two things together as capital N, so it becomes capital N plus alpha plus beta minus 2. Is that clear? So for our running example of this coin toss thing, right? Like, so we assumed that alpha is equal to beta is equal to 5, right? So then P map becomes n1 plus 4 divided by capital N plus 8. Okay. Now, okay. So now you see that this again looks very similar to the maximum likelihood estimation, but with one big difference. So the difference is I have plus 4 and plus 8 here, right? Initially, when I have no evidence, like so when I haven't seen any trials, okay, then this is 0, this is 0. So my theta map, like the P map, is going to be 4 by 8, which is 0.5, right? So when I haven't seen any examples, then map tells me that the probability of seeing a head is 0.5, which is what we wanted, right? Now let us say I see one example, and that example is head. Now in MLE, the probability of seeing head is going to become 1 immediately, right? In this case, it is going to be 1 plus 4, which is 5, divided by 1 plus 8, so 5 by 9. So 5 by 9, I think it's greater than 4 by 8, yeah. So 5 by 9 is like something like 0.5 something, right? So your probability, your belief about getting ahead just increases because you saw one. Okay. Now let's say we see only head. Okay. For 10 times we only see head. Now what happens? It becomes 10 plus 4, 14 by 18. So now you see that this probability is actually approaching 1, right? So there are many nice things about this setup. Okay, so the first nice thing is you can set up an initialization. You can say I want the initial belief to be this. Okay, and the other nice thing is if your belief was wrong, then as you get more and more data, that belief is going to be like suppressed down. Okay, so when you have infinite amount of data, then this 4 by 8 doesn't matter anymore. Okay, so but we can also play it the other way around, right? Like, so for example, let's say you have a very strong belief that you don't want to be suppressed by the data. Then you could set alpha and beta to be very high value. You could set alpha and beta to be 1,000. Like now it is going to take lots of examples to get out of this 0.5. Okay, so in some sense, this P map is pulling your predictions to your belief, but it let it go, like the belief, like if the data says